Imagine you're standing in front of a photo of a vibrant Thai green curry, and you want to find the recipe. You upload the image to a smart food app. It returns a dish that's almost right, similar ingredients, same color, same general shape, but it's missing one key detail: the kaffir lime leaves that give the dish its unmistakable aroma. Now imagine the system could see that missing ingredient, not because it's visible in the image, but because it should be there based on the cooking process, the cultural context, and the subtle cues hidden in how the dish was prepared. That's the power of what we're about to explore. Today, we dive into a groundbreaking new approach to image-to-recipe retrieval, one that tackles a deep, often overlooked flaw in how AI models understand food: representation bias. This isn't just about matching images to recipes. It's about understanding them, not just what they look like, but what they are, in a way that respects culinary nuance, cultural diversity, and the invisible details that make a dish truly unique. Let's start with the problem. The hidden flaw: why images lie. Current AI models for food retrieval assume that a photo of a dish contains all the information needed to find its recipe. But this is fundamentally flawed. A food image shows you the outcome, the final plated dish. It doesn't show you how the ingredients were prepared, how they were combined, or even what was left out. For example, salt. It's invisible after cooking. Marinating. No visible chain. Tempering spices. A fleeting moment, not a visual feature. Yet these are critical to the recipe. They define the flavor, texture, and cultural identity of the dish. So when models learn to align images and recipes, they naturally overemphasize what's visible: the large ingredients, the obvious cuts, the dominant colors. This creates a representation bias. The model learns to prioritize what's easy to see, not what's important to know. And this bias gets worse when you move beyond Western cuisines. The multicultural challenge. Now imagine training a model on recipes from Indonesia, Thailand, Vietnam, Malaysia, and India. 5 rich culinary traditions with distinct flavor profiles, ingredient preferences, and cooking techniques. These cuisines share some ingredients: rice, garlic, chili, but also have unique ones. Vietnam: rice paper fish sauce. India: tempering garam masala. Malaysia: balak and pandan leaves. And cooking actions: Thailand: stir-frying with a wok. India: slow simmering with ghee. Indonesia: wrapping in banana leaves. But here's the catch: a model trained on mixed data can't tell which actions or ingredients are unique to which culture. It sees a dish, recognizes a few common elements, and defaults to a safe match, often pulling a recipe from a different culture entirely. This isn't just a technical issue. It's a cultural one. It risks flattening the rich diversity of global food into a homogenized, visually driven model. The solution: causal inference for food. To fix this, our team at Singapore Management University introduced a causal framework, a way to reason about cause and effect in cooking. We asked, what causes a recipe to exist? Answer: ingredients and cooking actions. And what causes a dish to look the way it does? Answer: the same ingredients and actions, but only the visible ones. So we model this as a causal graph. Ingredients and cooking actions are confounders. They influence both the recipe and the image. But because not all ingredients' actions are visible, the model learns a spurious correlation. It assumes that if something isn't in the image, it's not important. To fix this, we apply a technique from causal inference called backdoor adjustment. Instead of letting the model compare images and recipes based on what it sees, we intervene. We remove the influence of visual visibility. We ask, what would the similarity score be if we could see the full recipe, regardless of what's visible in the image? Mathematically, this means we adjust the similarity measure by weighting it with the true distribution of ingredients and actions in the recipe, not what's visible in the image. The result: a new similarity function that says, even if salt isn't visible, if the recipe says it's used, it should still matter. How it works in practice: we built a 2-part neural module that predicts what's missing and injects that knowledge into the model. 1. Ingredient debiasing module. Takes the image embedding as input. Uses a transformer decoder to predict which ingredients are likely present, even if invisible. Then retrieves their embeddings from a culture-specific ingredient dictionary. Weighted by predicted probability, these embeddings are added to the image representation. 2. Action debiasing module. Takes the predicted ingredients and uses a conditional generator to predict the cooking actions associated with them. For each ingredient, it generates a sequence of actions, e.g., chop, marinate, simmer, and retrieves their embeddings. Again, these are weighted and added to the image embedding. This creates a richer, more complete representation, one that reflects not just what's visible but what's intended. And because we use culture-specific dictionaries, each cuisine gets tailored treatment. Indonesia gets its banana leaf and tempeh. India gets its tempering and garam masala. Vietnam gets its rice paper and nuoc cam. This ensures that the model doesn't default to a one-size-fits-all approach. Results that matter. We tested this on 2 datasets. 1. Recipe 1M, a standard monolingual dataset, mostly Western cuisine. 2. Our new multicultural dataset, 73,000 image recipe pairs across 5 cuisines, curated from Cookpad using Wikipedia dish lists. On monolingual data, adding just ingredient debiasing improved recall by 1%. Adding action debiasing helped but less. But both together boosted performance across the board, improving median rank by 1 on the 10K test set, and increasing recall at 1 by up to 5.6%. Even better, zero-shot retrieval, where the model sees a dish it's never seen before, showed dramatic gains. For example, a pizza query was being confused with frittatas and pies. With action debiasing, the model recognized baking, spreading, and preheating unique to pizza, and ranked it correctly. On multicultural data, this is where it truly shines. Using OpenClip as the base model, we saw a 15-point drop in median rank when using both debiasing modules. For low-resource cuisines like India and Vietnam, where training data is scarce, the improvement was even more dramatic, with median rank dropping by over 100 ranks. The model's performance with a culture classifier, predicting the culture of the query, was almost as good as the Oracle, which knows the culture in advance. This proves that our method doesn't just improve accuracy, it levels the playing field for underrepresented cuisines. Why this matters? This isn't just about better recipe retrieval. It's about building AI that understands food as culture, not just pixels. By using causal reasoning, we're moving beyond surface-level similarity. We're teaching models to reason about cooking to ask, what's missing? What's implied? What's unique? And in doing so, we're making AI more fair, accurate, and culturally aware. Final thoughts. The future of food AI isn't just about recognizing what's on the plate. It's about understanding what went into the plate, the invisible ingredients, the hidden actions, the cultural stories behind every dish. Our method, causal backdoor adjustment for cross-modal representation learning, is a step toward that future. It's lightweight. It's plug and play. It works with existing models like HT, T-Food, VLP Cook, and multilingual clip variants. And it proves that when we teach AI to think causally, it learns to see deeper. So the next time you search for a recipe from a culture you've never tried, or even one you've never heard of, you can trust that the AI won't just guess. It will understand.